Okay, everybody. In this video, I'm going to do another problem for you. I'm going to do a problem called the spherical pendulum using Lagrangian mechanics. And then we're going to talk about the method of Lagrange multipliers and how you use them. Okay, so the spherical pendulum, it's also called the bar of soap in a bowl problem. So basically, it's a pendulum that can move in 3 dimensions, but you would get the same result if you took a bowl, and a spherical bowl, half of a sphere, and you let a slippery bar of soap roll around in it. So it's a pendulum that can move around in 3 dimensions and back and forth in any direction. So we're going to assume it has a length, here's the mass, length L. So we want to ask the questions, A, how many degrees of freedom do we have? B, what's the Lagrangian? C, I'm going to ask to find the generalized momenta. And if any of the generalized momenta are conserved. Okay. So, how many degrees of freedom does this have? So let's just say if I go straight down the center to here, this, whatever the support is, this length of string, of cord, makes some angle theta with respect to the vertical. So there's at least 1 degree of freedom. And now, let's say I have this, the x direction. There's some angle this way that if I draw a line straight out to the mass here, there's an orientation in this direction, I'll call phi here. So, as far as I can see, there are 2 degrees of freedom, and I'm going to call them theta and phi. So, I need to write the kinetic and potential energy for this. Now, this distance would be L cosine theta. This distance here is L sine theta. I'll try to write that down here. Let's start with the potential energy. It's going to be, I'm going to say potential 0 down here at the bottom of the bowl. So when it's up here, that's going to be mg, and that height is going to be L times 1 minus cosine theta. We've done that before with the pendulum. So pendulum's here. If it swings down here, this height here, the whole thing is length L, so the whole L and then minus L cosine theta. Okay. Kinetic energy. Well, the speed, say in this direction, in the theta direction, that direction, it makes an arc length L theta, so it has a kinetic energy 1/2 m L theta dot squared. And then it can go in the phi direction too, and the velocity in the phi direction, so maybe I'll write it, velocity in the theta direction is L theta dot. Velocity in the phi direction would be L sine theta, and then if I took the time derivative of that, or phi, I'm sorry, phi, no, it's L sine theta is the length, and then phi dot, because phi is the angle in that direction. So I get plus 1/2 m L sine theta phi dot squared. So there we go. So I have the Lagrangian. Minus there we go. So I like to take the partial with respect to everything I know I'm going to need. Partial with respect to theta is going to be ml squared sine theta phi dot squared cosine theta when I take the derivative of the sine. And minus, here I'm going to get an mgl sine of theta. Okay. Partial of L with respect to theta dot. That's an easy one, ml squared theta dot. And then the partial of L with respect to phi is 0, because we don't have phi in there. And the partial of L with respect to phi dot, that's also pretty easy. That's ml squared sine squared theta phi dot. And then if I take the time derivative with respect to that, what is that going to be? That's going to be 0. So you may ask, why is it 0? Well, it's because that's equal to dl d phi, and we know that's 0. So this implies that this quantity, ml squared sine squared theta phi dot, is a constant. And that is our generalized momentum P phi. But since dl d theta is not 0, then this is not a constant. This is, oh, I'm sorry, this is P of theta. It's not a constant. So we've done A, we've done B, we found the generalized momentum, and we have found D. Now I like to always in the end try to get my acceleration of my coordinates, generalized coordinates. So I like theta double dot, for example. Well, what is that going to be? Well, here's how I would get that. I go to the fact that d, dt, dl, d theta dot is going to be, here's dl d theta dot, take the time derivative of that, I get m l squared theta double dot. But what does that equal? That equals, which is the m l squared sine theta phi squared cosine theta minus mgl sine theta. So you can see that I can get divide by ml squared, and I get theta double dot. So theta double dot is going to be sine theta cosine theta phi dot squared minus g over L sine theta. So there's the equation of motion for there's theta double dot. And then we know, because the momentum of p sub phi is a constant, we know this implies that phi double dot is 0. Okay. There's the bar of soap in a bowl problem, otherwise known as the spherical pendulum. So let's talk about the Lagrange multiplier method. So what I'm going to do is show you how to use the method. And if you want to look in your book, it'll talk about how you come up with the equation that I'm going to use. But I'm just going to talk about the practical side of using the Lagrange multiplier method. So basically what the Lagrange multiplier method is if you have a holonomic constraint, we usually use that to get rid of one of the degrees of freedom, one of the coordinates. Not one of the degrees of freedom, but one of the coordinates. And in the Lagrange multiplier method, the Lagrange's equations you have for each coordinate are not independent of each other. We don't use the equation of constraint to get rid of one of the coordinates. So let's just state it here and then let's apply it. So let's say we have n generalized coordinates. Not the number of degrees of freedom, we have n generalized coordinates, and we have m equations of constraint. Then you'll have n Lagrange's equations. Then you'll have n Lagrange equations that will look like this. So they're going to look like dl dqi, this is for the ith coordinate, minus d dt, dl dqi dot, plus, then you're going to have m of these terms. So we'll go from j equals 1 to m lambda, which is a constant, and we call the multiplier, that we'll have to find, times the partial of f. So f is an equation of constraint. I should write that up here. We have Q1, Q2, Qn, T equals 0. So J equals 1 to M. So we have dF. This is the jth equation of constraint. The partial Qi. So this is for coordinate Qi. This is what we would have had for the Lagrange equations, and we have M terms here. And we'll have M constant multipliers if we have M equations of constraint. So let's say, for example, we have two generalized coordinates. So n equals 2, and let's say we only have one equation of constraint. So that means there's really 1 degree of freedom. But we'll have two Lagrange's equations now. We won't get rid of one of those coordinates using the equation of constraint. So we'll have this. Plus one term, so we'll have one Lagrange multiplier because we have one equation of constraint. F is the equation of constraint. I forgot to put equals 0 up here. And then we'll have another one for the other coordinate. And remember, the equations of constraint are written like this. Everything on one side of the equation equals 0. So these are for holonomic equations of constraint. Okay, now what is this term here? This, the sum, j equals 1 to m lambda j dfj dqi is, I gotta be careful, it's a generalized force. But just like our generalized coordinates don't have to have units of length, this generalized force doesn't have to have units of newtons. It could be, for example, torque. Okay. So that's the nuts and bolts of how to use this. Let's do an example or two to put it in practice. Okay. So, Lagrange multiplier method. So we're going to use that for this problem we know of as the Atwood machine. Here's like a ceiling. Here's a support that doesn't move. And we have a pulley here. Okay. So we're going to simplify things like we did back in your beginning physics. We're going to say our pulley does not move. Just because I want to simplify it a little bit. Pulley doesn't move. It's massless. Massless pulley. What else? Light string wrapped over it. Meaning we don't have to take into account the kinetic energy of the string. So we have this string wrapped over it, and there's frictionless. It's frictionless. Can't forget that. Okay, so on one side we have mass 2, And on this side we have mass 1. And what else? Well, let's say that mass 2 is greater than mass 1. Okay. Now, the length of the string is L. So what I'd like to do is find the Lagrangian for this. I'm going to use the method of Lagrange multipliers, so I want to find Lagrange's equations for this. Using the multiplier method. And then I want to find the tension in the string. That's going to be one of my generalized forces. So this is why you want to use the Lagrange multiplier method if you actually want to find out what the forces are, or the torques. Okay. Okay, well, I have a distance, I'm going to call this y1, and it measures where mass 1 is, and over here I have y2. So it looks like I have two generalized coordinates. Do I have an equation of constraint? There, of course, y1 and y2 are related, right? So y2 should be, well, if I add up y2 and y1, if I subtract L, it should be equal to some constant. So whatever y2 is and y1, if I subtract the length from this, it ought to equal some constant, so which I'll just call C. So I'll have y1 plus y2 minus L minus C equals 0. That's good enough. Okay, so that's my equation of constraint. So I have one equation of constraint, and I have two generalized coordinates. This is exactly like the example. N equals 2, m equals 1. So let's first find the Lagrangian. 1/2 m y1 dot squared plus 1/2 m y2 dot squared minus the potential energy. Now I'm going to just say the potential energy is 0 at the very top, so negative mgy1 and negative mgy2 is a potential energy, so I'll put plus because I'm subtracting the potential energy here. M1G, oh, this should be M1 and M2. I got to be careful here. Those are two different masses. So that ought to be my Lagrangian. So one Lagrangian equation is this. I only have one Lagrange multiplier because I only have one equation of constraint. So let's go ahead and do this. dl dy1 gives me m1g, and then dl dy1 dot will give me m1 y1 dot, and then I take the time derivative, so I get minus m1 y1 double dot plus lambda 1. So I'm just going to, since I only have one lambda, I'm just going to go ahead and put the 1 there. The partial of f with respect to y1 is just 1. So there you go. There's one of my Lagrange equations. The second one, dl dy2 minus derivative with respect to time of dl dy2 dot plus lambda 1 df dy2 equals 0 equals dl dy2 is going to be m2g. I'm going to have minus m2 y2 double dot plus lambda 1 and 1. So there's my two Lagrange equations. So I have two equations, and how many unknowns? Well, what I'm really after is lambda 1 right now. First of all, I want you to notice that this term is the same for both of these. So this is the force. This is the generalized force on our masses. So this is going to be the force on mass 1, force on mass 2. These are the tensions. So let's see what we get. Okay, so how am I going to get lambda? So if I look at this first equation, I can solve the acceleration for mass 1. And what will I get? I'll get this side 0, so I bring that over and leave this stuff here. I get it's going to equal g plus lambda over m1. So that's y1 double dot. But I know that y2, if this, I guess I thought this one was going down, this one's going up, whatever the acceleration of this one is, the other one's negative of that. So what I do for y2 here, I stick in this. So I get m2g minus m2 negative g plus lambda 1 over m1 plus lambda 1. And then if I solve for lambda 1, this is 0, by the way. If I solve for lambda 1, then I'm going to get lambda 1 is negative. I'll end up with 2m1 m2g over m1 plus m2. And you can double check me on that. So I told you this is the force. So that's the tension in our string. So if mass 2 is going down, the tension in the string on it is going to be up and equal to that in magnitude, and if this one's going up, the tension's down. So why do we identify it as the tension? Is because, let's say I look at one of these, I know the force down for gravity is m1g. The one I don't know, which is a force between these two. This way you have the equation of constraint because you have a relationship between these two. So the force between these two is going to be your generalized force. And I have to realize, well, that's the tension force. Let's do another problem. So let's do one we've already done before. So we did the yo-yo problem. Let's do that one. So we have this yo-yo. It's on the end of a string. Radius A. Some angle theta. For the orientation, it has mass m. So I think we had two generalized coordinates. Y and theta, and we have an equation of constraint. Our equation of constraint was that f y theta is equal to, well, how far does it go down in y? Well, it depends on the arc length as it moves through angle theta. So that's not our equation of constraint. Our equation of constraint is equal to y minus a. Theta is 0. Okay? So we have two generalized coordinates, one equation of constraint. So what will our generalized force be? It will be the tension in this string. Okay. Or it will be the torque. If we find the generalized force for y, it'll be a tension in the string, and generalized force for theta, it'll be a torque. So let's find our Lagrangian. It's 1/2 my dot squared plus 1/2 I theta dot squared, the rotational kinetic energy, minus mgy is the potential, so plus mgy. Because again, the Lagrangian is kinetic energy minus potential energy. Okay. So our two Lagrange equations are, so first of all, when we take the partial of the constraint equation with respect to y, what are we going to get? We're going to get 1. And if we take it with respect to theta, we're going to get negative a. So our Lagrange equations are going to become, I guess I'll write them down, dl dy minus d dt dl dy dot plus lambda times 1 equals 0. And this is going to give me dl dy is mg. So I'm going to get mg minus my double dot, that's this term, plus lambda equals 0. And the other one, dl d theta minus d dt dl d theta dot plus lambda times negative a equals 0. But that's going to now equal theta. When I take the derivative with respect to theta, I got 0 minus, hold it, I gotta be careful here. Yeah, I get 0 minus the derivative with respect to theta dot is just I theta dot, and then I is a constant, so when I take the time derivative, I'll get I theta double dot minus lambda a is 0. So I have these two equations. Okay, well, I'm going to look at this equation here, and from that I'll get lambda is equal to negative I theta double dot over A. And now I'll substitute that into the other equation. Equation 1, equation 2. So then I'll get mg minus my double dot plus negative I theta double dot over A. Well, that's not what I want to do. Okay. I have this. What do I want to do with that? I know what I is, by the way. I was 1/2 ma squared, the moment of inertia for this disk of radius A. What else could I do? Also, since I have that equation of constraint up here, I also have, which is y minus a theta is 0, y double dot is a theta double dot, right? So now I can use that if I wanted to, just to replace this theta double dot with y double dot over a. So I get lambda is negative 1/2 ma squared over a and y double dot over a. So if I do that now, I'm going to plug that into equation 1. And I'm going to get then mg minus m y double dot is equal to negative 2 lambda over ma. No, I got a squared on the bottom here, a squared on top, so just m. So 2 over m lambda and the negative sign. Yeah, so now up here then I'll put in negative 2 lambda over m. And then plus lambda equals 0. M's cancel out there, so I get mg plus 2 lambda plus 2 lambda plus lambda equals 0. So I get 3 lambda equals negative mg. Lambda equals negative mg over 3. Okay. So what do I get? The generalized force for y is lambda df dy equals negative mg over 3, and df dy is 1. So that's the tension in the string. And q theta, lambda df d theta, and remember df d theta was equal to, what did we say that was? That was negative a. So I'm going to get mg a over 3, and that's a torque. Torque on disk due to string. Okay, so there's a couple examples with the Lagrange multiplier method. So again, you find your generalized coordinates. You don't get rid of them with constraint equations. And when you find that Lagrange multiplier, that can be used to find the generalized force. The reason you use the Lagrange multiplier method is because you want to find generalized forces. So forces are torques. Okay. So that's the end of this video. The The next video we'll discuss Hamilton's equations. I might do another example or two using the Lagrange multiplier method also. So I'll see